So the next example, and we're asked to draw the bending moment diagram for the cantilever, which we've already done the shear force diagram for. And so just what do? We figured out the reactions first. It's built in, so it's got a moment component. So we figured out those reactions. And now that we know, we could have just drawn this shear force diagram straight off. So we just have gone up VA, so positive 3 kilonewtons. So we'd figured that out, that VA is 3 kilonewtons. Then we'd have gone flat between forces, and then we'd have come down 3 kilonewtons. That's what the shear force diagram is. The bending moment diagram, well, that's what we need to figure out now. So let's draw our axes first. So moments down the way. And what else do I know? I know what this is going to be. I know it's going to be 3 times 4, and so it's going to be negative. Why do I know that? I'll get to that in a minute. So this time it's going to be mostly negative, this shear force, the bending moment diagram, sorry. And so we'll just do the axis up here. So remember, positive is downwards for bending moment. And so we're going to have x in this direction in meters. And we're going to have moment, bending moment. Sometimes get lazy and just call it moment, but it's the bending moment. It's the internal force we're talking about. And this time we are in kilonewtons. Yay, won't make a mistake. So down kilonewton meters. I drew it on without really thinking about it, actually. If we do 5, 10, 15, but too small, I'll just move this down a fraction. I'm an idiot. You know that already, though. It's mostly negative. It's upside down. We're going to get it mostly negative. This axis needs to be down here. I might even just do it right down there. It's a bit of a funny looking. That'll do. It'll be fine there. So until we get a bit better at this, let's just use the method of sections first. Now we do know, so for shear force, it's a flat line between forces. We've already figured out that for moment, it's going to be a straight line between forces, but it might not be flat, it might not be horizontal. Well, it probably won't be horizontal, usually be inclined. I wonder if we could guess it. Nah, let's just do some first. And so the default is, if ever you're stuck or you don't know what to do, just do the method of sections. So use the method of sections at different points and just figure out what those internal forces must be. So that's what I'm doing down here. What I'm doing first is I'm just imagining moving a tiny amount from that support, just a tiny amount. So we're just going just slightly into the beam by like 0.0001 of a meter or something like that. So I've drawn on my reactions. I've drawn on positive to get positive internal forces. And we're going to figure out the moment. We've already done the shear. We'd know that it's going to be 3 kilonewtons always. That's what this diagram is telling us. Okay, so the shear force is always 3 kilonewtons. And so we could just put that on here. So this is always going to be 3 kilonewtons, the internal shear. This one too. Oops. Until you get to the force itself, and then there's going to be no shear after that. Okay, now, so the usual stuff. The sum of the moments is going to be 0. I'll take the moments about this point. That's just a tiny distance from the support. So the sum of the moments is equal to 0. That means we have got 12 in the positive direction, so 12 kilonewton meters in the positive direction, and we've also got m naught as in the positive direction to get a positive bending moment. Oh, it's m naught plus, so I'm just saying I'm just going a little bit into the beam. Is going to be equal to 0. Now, because this lever arm is so small, I'm just going to ignore, so this would be 3 times something extremely small, 0.00001, and so it's pretty much 0. And this one goes through that point, so it is 0. So therefore, m naught is going to be minus 12 kilonewton meters. Just solving that. So it's just kind of the it's like it's the opposite of the reaction here. It's just the opposite of that reaction. And you can almost think of it like this. So you got, let me just draw it. So for that tiny little section that we've got there, we've got 12 kilonewtons going this way, 12 kilonewton meters. And you've got 12 kilonewton meters going this way. And so the internal force there is the hogging one. And so you're going to get a negative moment because it's hogging. Okay, so you're always going back and just thinking about what these things mean to make sure that it all makes a bit of sense. Okay, we drew it on the positive direction. Because we got a negative, we know that that moment is actually this way. And therefore, we're getting this clockwise and anti-clockwise right, anti-clockwise left, clockwise right. Therefore, it's really a negative moment. Okay, so we're drawing this on positive so that if it comes out negative, it's got the right sign for that internal force. So we know we're starting up here. I'll just decide what these are. So let's just call this 3, 6. So we'll just say 3, 6, 9, 12, say, for the units. And we're starting up here. Now, what we could do now is we know it's going to be a straight line to the next point. It's not horizontal, that's the shear force. It's going to be an inclined line. So we could just jump to this point here and calculate what the moment is at that point, and then just draw a straight line between them. But just to be sure, because we haven't done many of these, let's just go through a few points just to see what's going on here. So we've now gone in 2 meters. The sum of the moments is equal to 0. Positive would be this way. Positive internal force. And where are we at now? We're at 2 meters. So therefore we are going to get, so we're going to have that 12 kilonewton meters to start with. And well, I don't know why I'm not drawing on a line, or because it's not in line, it's okay. So we've got this one, 12, it's going in the positive direction. Then we've got, if we're taking about this point, we've got 3 kilonewtons in the opposite going clockwise times a lever arm of 2 meters. So 3 kilonewtons, lever arm 2 meters, clockwise direction. And so therefore we're going to have minus 6. And then we're going to have M2 is positive direction plus the moment at 2 meters is equal to 0. So therefore M is positive. That's positive. I'm just checking my signs here. So that's positive. This one here is positive. This one is also positive. This one is negative. So we're going to have 6 plus M2 is 0. So M2 is equal to negative 6. And so at 2 meters, I haven't actually put on my, you can put them on here actually. So that would be 2, 4, and the end of the beam's at 5. 2, 4, 5. So at 2 meters, the moment is 6 kilonewton meters. Okay, along to 3 meters or 4 meters? I have done 3 meters. Yeah, well, let's just quickly do it. So sum of the moments is equal to 0. Positive moment would be this way. And this is the moment at 3 meters. Let me just rub this out. So therefore we're going to get sum of the moments equals 0. So let's think again. So we're going to do the moments about the 3 meter point. Is equal to 0. That means we have, so 12 kilonewton meters positive, 3 times 3, negative direction, so negative 3, looking at this one now, about this point, 3 times 3. The 3 kilonewtons at this end has no moment because we've got no lever arm. And then we've got plus M3 equals 0. That means that M at 3 meters is going to be 3 kilonewton meters minus. Yeah, got to be careful, eh? So all these are minus, 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 minus. Get rid of that, force of habit. And so M is positive in this direction. M is positive this way. So at 3 meters, we've got minus 3. Okay, down to 4 meters now. So positive bending means it's that way on that side. So the sum of your moments is equal to 0. That means we've got 12 minus 3 times 4. That 3 does nothing. We've also got, and the shears disappeared to 0 at that point. Minus 3 times 4 plus m4 equals 0. So therefore the bending moment at 4 meters is equal to 0. And then you could work it out for the last bit. So for 5 meters, so the sun, let's just do it. You kind of expect it to stay 0. And you'd really expect it to be 0 because you could take the other side for your method of sections. You could take that side and it's got no forces on it at all. And so on that side, you would draw the positive bending moment, would mean that you'd apply your external moment in this direction. And this is the moment at 4 meters. And so we could have taken the other side here. It would be 0, and it wouldn't matter where you did that along here. You've still got nothing on the other end, so it's just going to stay 0 until it gets to the other end. But let's just do the calcs. I can't even remember what we're doing now. So we're going to take it about here. It'd have to be just a little bit in from here, if you know what I mean. So it would have to be a moment of 5, but a little bit less than 5 meters. Otherwise, you're not in the beam anymore, so there is no internal forces. So the sum of the moments is equal to 0. So we've got, even if we come from this other side, 12 and positive minus 3 times 5 this time, plus 3 times 1. Sorry, minus 3 times, plus 3 times 1, that's right. Plus moment at just a bit less than the end of the beam is equal to 0. So we've got 12 minus 15 plus 3 is 0. So m5 to minus 1 equals 0. Just less than 5 meters is equal to 0 kilonewton meters. And so it stays 0 after that because there's just nothing happening. No loads, no moment. Okay, and we could just draw that. Oops. Sorry about that. Slight technical hitch. So you can imagine that it's just going through like this. Gets to here, and then it goes flat after that. Stays at 0 after that. And you can shade that. And that's you've got your bending moment diagram. Now, we could have figured that out from the shear force diagram. So the change in the bending moment diagram is just equal to the area under the shear force diagram for the same distance you move along. So for every 1 meter, so this is 1, 2, so every 1 meter I move along, it's going to change by 3 kilonewton meters, the area in here. And so for each meter you go along, it's going to change by 3 kilonewton meters, just the area under the shear force diagram. This is positive, but this is going in the positive direction. Okay, it's starting very negative, it's going in the positive direction. And then you get to here, there's no area under here, and so therefore it's not changing at all. And so we could have figured that out just by looking at this shear force diagram. We could have got to this bending moment diagram. Okay. I think that's all I want to say about that. The other thing we could have done is, rather than calculate all these intermediate points, we could have just calculated the moments at just near the start, and then where that first force was applied, and then at the end, and just draw straight lines between them. So they're going to be straight lines between forces. They're not going to be horizontal like the shear force diagram was, but they are going to be straight lines.